Hello! Today's Monday, February 1st, and this is Digital Image Processing 1, 637, and we'll be picking up on tomography today. There are a few, I don't know if there are any, I know there's at least one question that I'm going to answer, but I don't know if there are other questions, and also let me just, I saw some questions in emails and things. I think, how many people in here have successfully gotten the seek to compile with the makefile? Okay. Are there people who are still struggling? Okay, so at least among this group, people feel like they were able to get that, maybe, although some people may be timid. But, so this is other people, I mean, that's a good sign. If you're having problems with that, honestly, my best, here are my suggestions. And there may be other suggestions that are better. Well, the first suggestion covers me, which is post something on Piazza and see if some other student can help you. Honestly, that's the best thing you can do. That's likely to be like your first line of defense, you might say. And then also you can email Wen Ree, this TA, and CC me. Actually, there's a number of other students who are former they're alumni of this class, which I have listed, I think, with their email addresses. You can email them. If you email some of those people, you might want to CC me just so I know what's going on a little bit. But they're actually better at answering questions than I am because they're more on the front lines. But Piazza, I think, is actually a good way to get questions answered, and then whatever answer you get, other people can see too. Because usually, if you have a question, other people have a similar question. The one question I saw was a person who was having trouble. They were saying, well, they couldn't get the C part of the lab to work. Well, first of all, I should say this. If you didn't get the lab done, don't worry. You can keep working on it, but start working on the other. Don't get too far behind. So you can turn them in late. That's fine. Maybe I shouldn't tell you that because you have to be careful not to get too far behind. But you can. But here's the thing. If you get hung up on one lab, don't be a perfectionist where you just won't proceed until you get that one done because that's going to hang you up. Start working on the next ones, okay? And then you can work on more than one in parallel. And then as you get your questions answered, you get unhung up on whatever's hanging you up, then you'll get that done and move on. But sometimes students will be like a little bit too much of a perfectionist, and they'll like say, well, I can't move on until I resolve some question. You have to do parallel processing a little bit, okay? And if you can also, if there's like one thing that you don't know how to do, you can put it aside while you're asking the question with the idea it's mostly done, and you just have to fill in that little piece. And then when that piece is filled in, then you can turn it in, okay? But remember, the main objective is for you to learn the material. And Wen Ree can help you if you're hanging up. But I saw one question where a person was having trouble with the C part. And I think, it was hard to read between the lines because you get little bits and pieces of information, but you're not really experiencing what they're experiencing. So it's guesswork. But it sounded like maybe the C was working, so it was compiling, but somehow it wasn't producing the output that they should or something. So if it's compiling, really most of the battle is won, okay? That's more of a thing where you're probably a little confused about how to use the command line interface, or the data is getting put in some directory that you don't know where it is, or you're a little lost, okay? And you'll eventually figure that out because a lot of that has to do with the culture of interacting with the computer through like a bash shell, which is, an important thing to learn. So now, okay, so Kenny, you had a question, which is the 2D random processes. I assume that the 2D random processes lab is due on Friday? Okay. So a few things. First of all, because of the pandemic, the schedule's a little messed up. So the sequencing of things may be a little different than they would normally be. But maybe not too much different, I don't know, but it could be. But in any case, the labs often get ahead of the lectures, okay? So if you feel like, so part of that is it's a chicken and egg thing. I actually think doing the labs can be helpful so that when you come to the lectures, You really absorb the material fully. But on the other hand, you may not really know how to do the lab, so you're a little bit lost. So if you want to do it to the best of your ability and sort of set it aside and then turn it in later when you feel like you got your questions resolved, that's fine. But don't let it go too long, like I said. The thing you don't want to do with this class, because the labs come kind of fast and furious, especially towards the end, that you don't want to let it get too far ahead of you, okay? Especially because this semester we don't have a spring break, right? So I know I use spring break to catch up. I'm sure a lot of people do that, right? So be careful not to get behind, okay? Not to get behind. And if you don't know how to do something in the labs, ask, right? Remember, it's fine to talk to other students about how to do it. It's just that the final implementation should be yours. Basically, you should be typing in the code, and it should be your code. I mean, you shouldn't. But, in terms of, my goal is for you all to understand it and do the correct thing. It's not like supposed to be a secret, okay? I'd be happy to tell you how to do it. In fact, I know it's a little different for people who are here, but if you want to stay a little bit after class, I can often answer some questions quickly after class too. Or if you really get stuck, like I said, you can email me, CC Wenri, okay? Because he knows what's going on better in some ways. Okay, are there any other questions? Okay, so let's pick up maybe on the tomography material. Did I answer your question, Ken? Okay. All right, yes. Tomography. Okay, so tomography is tomography is cool. So there's two topics I want to cover: tomography and MRI. And the reason I want to cover those two topics is because both of them we can do without actually doing discrete time. In practice, of course, they're implemented in discrete time because they're done on computers. But at least the formal theory of it, I can explain without using discrete time. I can explain it all in continuous time with the continuous time Fourier transform. So we can move on. I think it's more interesting when you're talking about applications. So it kind of breaks it up a little bit. And tomography. So hold on, let me kind of go ahead and show you this. I know I have a picture somewhere. This is what's called a CT scanner. People confuse CT and MR scanners. Why? Because they both basically look like big white donuts, okay? So a CT scanner stands for computed tomography. And MR scanner stands for magnetic resonance imaging, okay? So these used to be called CAT scanners, or for computed axial tomography. But they're not axial anymore. Now they're helical scans. So doctors often still refer to them as CAT scans, but they're really not CAT scans. They're CT scans. Sometimes they call them VCT, for volumetric CT, because they're, we'll talk about it a little bit, but they just used an axial rotation, and then they went to a helical rotation, and then they went to a multi-slice helical rotation. So the multi-slice is basically 3D, so it's volumetric. We won't really talk about that. So sometimes that's what they call them. And the upshot is this, that they can take a picture of the inside of your body, okay? And before they had CT and MR scanners, CT scanners were widely available first. And even today, I think CT scanners are much more widely used. CT scanners, they cost maybe $500,000 to $1 billion. For a hospital, that's not a big expenditure. So, yeah, I know it sounds like a lot of money, right? But and you can buy inexpensive CT scanners, like you can buy used CT scanners; they're inexpensive. But $500,000 you can easily buy. I think you can easily buy a CT scanner. The really high end ones are more expensive, so the hospitals buy these all the time and replenish them. It's like getting an inkjet printer, okay, for them, okay. So they're inexpensive scanning modalities, and The MR scanners tend to be more expensive. Not just the scanner. The scanner's like twice the price typically. But it's not just that. It's the sighting of the scanner, and which is much more expensive. CT scanners you can put anywhere pretty much. Just drop them into a room. But an MR scanner is expensive to sight. You have to have special shielding and everything. And then also the CT scanners scan very quickly. So you can scan a lot of patients in a day. In some countries, not in the U.S., the flow of patients is somewhat limited because there are other reasons, but part of it is just patients don't like to be hustled around. But in some countries, they'll scan a patient every 10 minutes. Okay, so they have and the point is that the cost of the scan in terms of the capital expenditure is this is basic finance. It's the capital expenditure times the financing cost over the period of time. I mean, it's the financing cost, which is proportional to the capital expenditure, divided by the number of patients that you have to scan. So if you can scan 3 or 4 times the number of patients, effectively the cost of the scan is 1/4, right? So CT scanners are pretty inexpensive. I mean, when you get the bill from the insane healthcare system we have, it can be for any amount of money. I've seen bills where the CT scans were I don't know, some ridiculous number. I'm thinking, was it $10,000 or something, or $1,000? I know it was some ridiculous number like that. But the actual cost of doing a CT scan is a few $100s maybe. So it's just the insane healthcare system. So they like to use these because they can use them for a lot of simple things. The downside of a CT scanner is that you have exposure to X-rays. And that it's not good for diagnosing certain things. It's good for it's basically good for scanning anatomy. And it tends to be not as good for soft tissue as it is for some other things. MR's better for some soft tissue sometimes, and it's particularly good for neuroimaging because it's not necessarily anatomical, it's functional, okay? And there's also a thing called PET scanning, which is algorithmically similar to CT. But PET scanning is a functional imaging modality. But CT is the most widely, basically, if you break your leg, they might just do a CT scan today. They can do a planar X-ray, but they'll often just do a CT scan so they can get a better idea of what's going on. But the key issue is this. Everybody likes to pick on medical imaging as a way of this thing that, maybe it's not so much in vogue. There was a point when it was very much in vogue to pick on medical imaging as a way of raising healthcare costs. But, sure, you spend a lot of money on medical imaging, but it drives healthcare costs down dramatically because before they did this, they used to have to they did a thing called exploratory surgery, where they just kind of cut you open and were searching around to see what was going on. I mean, it doesn't sound like a really great idea to me. They did that. They still do that once in a great while when they're really desperate. But for the most part, they can really diagnose all kinds of crazy things. Very general diagnostic instrument by using CT because they can, So it's a miraculous innovation, is my point. And it's miraculous because it's non-invasive, right? They can see and it's not just for medical applications. CT is playing a huge role in things like manufacturing. So there's a LEAP engine plant in Lafayette, Indiana. Does everybody know what the LEAP engine is? It's the engine on the ill-fated, not the ill-fated, on the challenged, I'm going to get myself into big trouble here, on the challenged 737 MAX, But it's a great engine. It's super fuel efficient and everything. It was sort of like the airplane was designed around that engine, which is a major innovation. And it's made through a consortium between Safran and GE. And my point is this: those engines are incredibly technologically advanced, and one of the really important components is the turbine blades. Because if you have taken a thermodynamics course, which you should, you'll find that the efficiency of an engine is related directly to the combustion temperature. So higher combustion temperature, higher efficiency. But if the combustion temperature is too high, you melt the engine. So those blades are made out of things called superalloys, which are like single crystals of metal that are designed to actually get stronger as they get hot. So, and they're incredibly sophisticated with the cooling mechanisms that they use and so forth. So they have to make sure each one of those fan blades is very precisely manufactured, because if it shatters in the engine, that's bad. That's what you have, an engine failure, which of course you don't want. So they inspect those, and they have to inspect them with CT, okay? Or if you go through the airport, that's a better example. Maybe every day you take, well, nobody goes to the airport anymore. Well, some people go to the airport. And you have to check your bag. It goes through a CT scanner to check, make sure there's nothing bad in it, okay? And that's another example. So manufacturing, security, science, the same technology is used in electron microscopy when you want to do 3D imaging of a virus or a, so that's how they get the structure of a coronavirus, of the coronavirus. The way they do it is by CT reconstruction of the virus. Okay, they get using an electron microscope. They get different views of the virus at different angles, and they reconstruct it. And another example is like in material science, you would reconstruct the grain structure of a metal so that you understand its physical properties, or you can design it to have particular properties by using CT. So CT is a really widely used, tomography is a really widely used technology, but perhaps the one that's most recognizable is the medical scan, because you may go in for this. The other, MR, is algorithmically fundamentally different. But tomography shows up in a very wide range of scientific, industrial, and medical applications. So it's really kind of cool. Now, what is tomography? Okay. Tomography is this. I mean, so you have like, in the old days, what they did is they had like, the old days being like, I don't know, like the 70s. They have a table here, right? And then you lie down on the table. Your legs are kind of long. No, the body is long, I guess. And what they do is they have an X-ray source over here. And the way you build an X-ray source, by the way, is what you do is you have the polarity is going to be a problem. You have a voltage source, a high voltage source, and you have two gratings. So there might be like 100 kilovolts potential between these. So this is a very high voltage source. But there's very little current, because it's a vacuum tube. This whole thing is in a giant vacuum tube. So you put it in a vacuum tube. And then over here, you have like a light bulb filament. So this is a current source. And the light bulb filament gets hot, and it emits electrons. And then the electrons, okay, hold on for a second. So this would have to be plus, I guess. And this is minus. I might have it backwards. You have to be a little, okay. And basically the electrons go from the low potential to the high potential, okay, because they're negatively charged. So they go zip, okay. And if this is 10 kV, if that's 10 kilovolts, okay, then when the electrons pass through here, their velocity, they've picked up 10 keV of energy. So they're traveling really fast, okay? And then you fire the electrons, you focus them, and you fire the electrons at, this is a tungsten target. So the electrons hit the target, okay? And when they hit the target, they decelerate rapidly, right? And when they decelerate, if you remember Maxwell's equations, that, well, let me see. Maxwell's equations say that electric field is, well, I don't know. The bottom line is this. I'm going to mess it up. But when they decelerate rapidly, when you accelerate a charge, right, you create a electric field. And the electric field is perpendicular because it's a cross product if you look at Maxwell's equations. So the photons come out this way. So when you decelerate the electrons, they hit the target and they emit photons in a perpendicular direction. And then the energy of the photons is nominally going to be 10 keV. Okay? Now, one thing that's really interesting is that with photons have no mass, okay? So what happens is that because they have no mass, they always travel at the same velocity, which is the speed of light, unless they're going through a dielectric. But in free space, they always travel at the speed of light. Because, anything with mass can't travel at the speed of light, because you'd have to put an infinite amount of energy into it to travel at the speed of light. So instead, because they have no mass, they travel at the speed of light all the time. But then what happens is that their frequency, of course, photons have a wave and a particle nature. So the frequency, nu, okay, this would be in cycles per second or whatever, some kind of unit, this is frequency, which is 1 over the wavelength, is going to be proportional to the energy times a constant. And does anybody know what that constant is? What's the constant that relates frequency to energy for a photon? It's Planck's constant, h, usually. Now, the specific value of h depends on what units you choose for your problem, right? But, so, if you double the energy of the photon, you double its frequency, or you have its wavelength, okay? So, now, later in the class, we'll be talking a lot about visible photons. We'll talk about, light, particularly visible light. Visible light is in the wavelengths between like about 400 nanometers to about 700 nanometers. And remember, 1,000 nanometers is 1 micron. A micron is about 1/20th, 1/40th the thickness of a hair. Okay, so micron's pretty small, but it's not like ridiculously small. Like you can observe things that are a micron thick in real life. Like, for example, if you see an oil slick, okay, and you see a rainbow on the surface of the oil, that's because it's varying on the order of a micron, which is 1 micron is actually not visible light, but it's what they call near infrared. But roughly speaking, light has on the order of a micron kind of wavelength. So if the thickness of the film changes on the order of a micron, you'll see that as a rainbow, okay? So you can see physically, like, realize, to me, if you talk like an Armstrong, it starts to be hard to, like, really conceptualize. It's sort of very abstract, right? It's like, well, that's the distance between an electron orbital and the nucleus of an atom. Well, that's hard to experience in real life, I mean, at least for me. Maybe you differ, but a micron's something you can experience, right? I mean, it's small, but it's not ridiculous, okay? So the wavelength of visible light is on the order of a micron. But by the time you get to X-rays, which are also a form of light, the energy is so high, or the wavelength is so short, that now it's really starts to be a little bit weird. Like, 10 keV, I should look this up. Actually, I can make that a homework assignment. Look it up. The wavelength of 10 keV X-rays, I think, is probably on the order of a few Armstrongs. Check it. I think it's probably on the order of a few Armstrongs. So an Armstrong's, 10 Armstrongs are a nanometer, okay? So when you're getting down to Armstrongs, those are atomic differences in nuclei. It's sort of those kinds of distances. But the point is, when you get to X-rays, people don't talk about wavelength anymore. You could. You could talk about, and then their wavelength would be on the order of angstroms, but they talk about energy instead. That's sort of the convention. And a typical X-rays for a medical application, a typical X-ray would be like 100 keV for medical. Okay, so I'll write this down just for fun. So typical X-ray energies. So like 2 keV, that would be what you'd call like soft X-ray. That would be like they'd use those in scientific experiments where they had very thin materials that they wanted to penetrate and still get contrast. Like, and then like, 100 keV, this would be like a typical medical. They might be used lower, like I think keVs have been dropping over time. And then like 1000 keV, or that would be 1 MeV. This would be like industrial. I saw an example where GE had done a CT scan of an entire jet engine, not the LEAP engine, that's pretty big, but like a smaller jet engine used in a small aircraft, I think, and they have this gigantic CT scanner that's the size of a room, okay? And they like bring it in with a crane, okay? They put it on a table and they rotate the engine around. But to get the X-rays to penetrate through something that big, metal, by the way, metal's pretty absorbing of X-rays. You need very high energy X-rays that can penetrate through the metal, okay? So, obviously, generally speaking, very generally speaking, as the energy of the photon increases, it tends to have more penetrating power through materials, right? It kind of makes sense. But over specific ranges, that may not be true. So, for example, this glass shield here may be transparent to visible light, but may not be transparent to ultraviolet light, which is higher energy. In fact, if you buy windows for your house, they'll make them so they're not optically transparent to ultraviolet light, so that way you don't get, like, it doesn't heat your house, and also you don't get a sunburn sitting in front of the window, okay? So it's like a filter. You can have various optical transmittance, but sort of over the large scale, if you get to very high energies, they tend to penetrate materials better. So very high energy X-rays. My point is really what? Well, my point is partly just to teach you something about the culture of X-ray imaging, but also communicate to you that CT is really widely used, okay? And now coming back to the original example, the first thing that they did, and this is like at the time of Madame Dr. Curie, right? So she discovered X-rays, and initially people didn't realize they were dangerous, which was sad. So, and there's, but basically you take an X-ray source here. Initially they used to put a piece of film here, right? And, well, maybe it would be like a chest X-ray. So you get a single planar view through the material, okay? And then later, and it's actually relatively recently that this has changed, because the chemical X-ray films, just like photographic film, were pretty sensitive. They're pretty good, okay? And they're very high spatial resolution. In fact, for mammography, which is a similar kind of technology, they still probably use, I'm not actually exactly sure what the state of the art in mammography is right now, but 10 years ago they were still using film, because the film had very high spatial resolution and was pretty sensitive to contrast. But maybe the photon count was a little high, so it would expose people to more X-ray exposure. But this is getting replaced. It's being like in various, and in scientific applications like electron microscopy, people used film up until just a few years ago. But it's slowly being replaced by electronic detectors. So it might be either a CCD or a CMOS device, but also the other problem is trying to make something of sufficient size, okay? And X-rays can't be detected typically directly by electronic devices because the electronic device will just go right through the detector. So like if you have a silicon detector, a silicon device like a CCD, the X-ray, it would detect visible photons, great, but not so much X-ray photons. So they have to have what's called a scintillating device in front of it. I'll talk about this some more. It's like basically a crystal of some material that is dense to the X-rays that stop the X-rays. So the X-rays, well, otherwise they'll just pass right through. So they hit the scintillating material, and when they hit the scintillating material, either what they do is they emit photons at a lower energy, like you might, if you saw it, if you were in the room and you turned off the lights, and you had the X-ray source off, and of course you'd want shielding to make sure you're not exposed to the X-rays, you'd see that the actual scintillating material glows, okay? It glows, and that means that the photons of X-rays are hitting that, being re-emitted in a fluorescing process at a lower wavelength, so lower energy, that's invisible light. So you slowed those photons down enough that you can detect them on the CCD. Or sometimes what they'll do is they'll hit the crystal, and they'll be like in a photoelectric effect, and it'll emit electrons that will get detected. The point is you need something to slow the X-rays down, otherwise they'll just blast right through the thing, okay? So then you get an image, and the image kind of looks like this, using my great artistic abilities. Oh, wait, hold on. You wouldn't get the whole person. You just get their arms. You get their chest. Okay? So you'd see, okay? And if you zoom in, you know, you'd be like, I don't know what a person looks like. They look like, you'd see their backbone, you know, you see the rib cage. Looks like that, something like that, okay? Well, you get one view. Now, the problem is this. You'd be like, well, that's helpful. It's a lot better than nothing. But you're like, well, I can't really see what's going on there, okay? Because, like, the rib is in front of whatever it was I was really trying to look at, the spleen or the liver or something, right? Or the lungs. Maybe you're looking for lesions in the lungs. Maybe the person's a smoker. Don't smoke. It's not good for you, okay? But you're a smoker, and you're looking for lesions in the lungs. So you'd say, well, I could take the person and have them sit on their side, okay, and get a second view, and then you can kind of try to look at this too, right? But the idea in tomography is you take a whole sequence of views with the person at different rotation angles, and you let the computer reassemble the jigsaw puzzle of what the person looks like in 3 dimensions. So humans actually can do that pretty well. Like, it's interesting that too much fun today. You know, there's like scanners that, you know, when you go into the airport and there's 2 kinds of baggage in the airport. There's what they call checked baggage and carry-on baggage, right? The carry-on baggage is when you go through the checkpoint, you carry it with you, and you bring it into the cabin of the airplane. So they have 2 different inspection systems for those 2 systems. So for carry-on baggage, they just get a planar X-ray like this, okay? In fact, sometimes you can see it on the screen as you're going through, and they look for things with shapes that are not good, okay? But they're not able to really do analysis of the physical properties of the materials for the things in the bag. All they could do is look for things that have an undesirable shape, okay? So now they're actually slowly replacing planar X-ray scanners and carry-on with CT. But my point is that, so they have some scanners which are called multi-view, okay? And what they'll do is just have a couple of, so you have the bag going through here. Okay. That's your suitcase. And it's on a conveyor belt, okay? And then what they'll do is they'll have like a single X-ray source, because this X-ray source is expensive. And then they'll have like a set of detectors. I don't know how to draw it. They'll have one detector like that and one detector like that. They're usually L-shaped, actually. And what happens is, so each of the detectors gets a scan of the bag, but from a little different angle, okay? It's as if I have this like object here. So this is a random object I just happen to have. And you like look at it at different angles, right? And they have like a setup where they have a computer screen, right? Like this. And then you look at the different views of the object, and you have a little trackball here. You know what a trackball is, like a thing you can spin like this. And with the trackball, they'll take maybe 8 or 16 views, and you can spin between. You can use the trackball to look at the different views, right? Basically, to index through the view sets like a video, right? So it's the perception you get when you're looking at that thing, because I've done it before. It's like you've taken this thing, you're like Superman, and you can look through it with your X-ray vision, and you're going like this. And I can tell you what, when you do that, you can see much better what's inside of that suitcase, because your brain reconstructs the 3D representation of the objects inside of the suitcase. They're now no longer just in your mind superimposed. When you go like this, your brain can reconstruct a 3D model of what's like. And I look out into this room, I don't just see a planar image. I see people sitting at chairs, right? So my point is this. There's way more information in a sequence of views with the object at different angles. And the computer can reconstruct that. So tomography is all about the reconstruction of a 3D model of an object from multiple views. That's sort of what it is. And the word tomo means slice. So the idea now, but we'll start off by talking about the 2D problem, even though it's really motivated by the 3D problem. And in the end, most tomography problems are 3D. But you can start with the 2D. In the 2D, the idea is this. You have X and Y, you have some object. And you imagine you take a slice to the object. So it's now a 2D slice. And you view that object at different angles. And at each angle, each point on what's now your 1D view, now your 1D image is really just a signal. For each 1D view, the pixel is the integral of the density through the object. And then you want to take that set of views and reconstruct it to a 3D object. And the question is, can you do it? Well, the integration, now, so your function, your measurement is what I'm calling here P theta of R. Theta is the angle of the projection. R is the displacement from 0. 0 is important because 0 isn't just anywhere. 0 has to go through the center of rotation of the object. Okay? So there's two ways of thinking about it. And in fact, there's two ways of doing it. One is that the object remains still and the detector rotates around the object. The easier way to do it is that the detector stays still and you rotate the object. So in industrial applications, typically they'll rotate the object. So they'll have, like a turntable like this. And this thing is connected to a motor. Motors look like this, right? Oh, they have 3 wires coming out of them. And then they put the object over here. I don't know what the object looks like. It looks like this. I don't know. Okay. And then this thing rotates. And then the source is here, and the detector is here. Okay. Here's the general rule of thumb. For things that are dead, they rotate them. Okay. For things that are living, they rotate the scanner. Okay. And the reason is pretty clear. I mean, humans don't really like it if you do that to them. Okay. So you would have a very big customer base. So because you could it could be like an amusement ride you get at the circus or whatever. Or they don't have the circus anymore. Whatever it is that they have. You go in and they put you in a little tube with like pillows or something, and they'd spin you around. And there actually, I think, are some scanners that do that for mice, but even mice don't like it. They don't like to do it to the mice. So most small animal scanners are made so that the scanner rotates and the animal's still. And also, to do that is much more expensive because now you have to have some kind of mechanism where it gets complicated. Now the X-ray source has to rotate, and they call it a rotating gantry. Okay, we're having fun today. Okay, they have a rotating gantry, so they have all this junk on this thing, and they have it's an amazing mechanical engineering feat because they have this thing that weighs about it weighs about the same as a Lamborghini. Okay. A few thousand pounds, like it weighs like 2,500 pounds or something, and it rotates on this thing, okay? And now you're like, okay, if I attach a wire to this thing, what's going to happen? Like the wire's going to, wouldn't be good, right? And you say, well, what you could do is like have the thing spin around 360 degrees and then stop and spin back so the wire doesn't get all wrapped around. But you can't do that because this thing weighs 2,000 pounds. If you start rotating a 2,000-pound thing and just stop it all the time, could you imagine like you take your car? That's called a car accident, right? Where you can't stop it instantly. It's got a lot of momentum. Okay, so they have no choice but to keep this thing spinning around. So they have to build a slip ring here where they have essentially a wireless transfer at gigabit per second rates through this thing. I mean, it's just an awesome problem, okay? I mean, it's amazing. Actually, here's the other secret. Okay, I'm having too much fun today. Here's the other little secret, which is that if, when you go in to get a CT scan and you're sitting inside this little guy here and it goes, there's someone calls over like the little megaphone thing and they go, "Are you okay?" And you go, "Yeah, I'm fine." And they say, "Well, we're going to take the scan now." And you hear, "Woo!" Okay? That's, if you took the fiberglass cover off this thing, you'd be like, "I'm leaving this place," okay? Because
there's YouTube videos where they show how fast.
Yeah, that thing is like a bat out of hell, okay? Yeah. It's pretty scary, but everything's bolted down real tight. And if it did fall off, I think it would fly out, in a direction it wouldn't hit you, it would hit somebody else, I guess. But no, I don't know that that's ever happened before, but it's kind of a little bit daunting, or you might say. So anyway, so the slip ring thing is a major piece of technology. But but building a CT scanner for industrial applications is relatively straightforward. You just get a fixed X-ray source and a detector, and you put a rotation stage here, and you spin it around. You just have to have what's called an encoder, and mechanical engineers know this. It can measure the precise rotational angle of the table. And you also need to make sure you align all these things. Like this thing has to be perpendicular. You have to do a good job of making it so things aren't crooked, okay? Okay, but the key now is that you've done all that complicated stuff. In some sense, that's hard, but the risk is low, right? I mean, if you hire enough engineers, you can figure out how to build this crazy contraption. And it'll cost whatever it costs, but GE's really good at getting costs down because they know how to make all their manufacturing processes efficient. So the hard part of the problem becomes the signal processing. How are you going to take that data and turn it into an image, okay? And that's where people like us come in to play. So now you have this data. How can you take these views and reconstruct it into an image? Okay, I've talked about all this stuff. Oh, this is just a little more detail. I'm going to talk about the 2D case, but what really happens is that you have to do a 3D volume, and there's a helical. What really happens is that in the medical case, as this thing's spinning around, they have you go through at a linear velocity through the center. So the actual trajectory is really a helix, okay? And what ends up happening to make even things more complicated is that they don't just take one view, one slice at a time. They take there's many rows to the detector. So it's essentially like a very long, thin photograph they take. And now every year the photograph gets thicker. So initially it was like one row, then it was 4, then it was 8, 16, 64. Now a lot of the state-of-the-art scanners are 128 slices. And the advantage to that for the medical application is that they can image your heart in a single and actually a half rotation, a little over a half rotation. So they like to be able to do that because one of the growing applications for medical CT is cardiac CT, which is people used to go in for what they call, or they still do, go in for what they call angiograms or cardiac catheterization. So they put a catheter basically through your leg, usually I think your femoral artery, and they go up through your heart to image, and they put tracer in so they can see if there's blockage in your coronary arteries. But it's not really that great having somebody poke a little tube through your arteries up to your heart. So there's a lot of various risks. So if they could do the same thing with a medical CT scanner, that's better. But of course, medical CT, it's like the old story, which is that it works great if your heart's not moving. But if your heart's not moving, you've got other problems. So instead what you want is you want the scanner to run really fast. So the rotation speed of the scanner is a big selling feature. And if they could do the scan in a single half rotation, so if they have a really wide detector that covers the entire heart, they can do the image in a single rotation. But that requires 3D reconstruction, which we won't talk about. Okay, now here's the thing, that this part of the course everybody always ignores because they think it's not that important, but it actually is critically important. That actually a physical model for the absorption of the X-rays is they travel through a piece of material. See, the thing is that you don't really, this is pretty hopeful, it would seem, because you have a bunch of different measurements. They're linearly related to the unknown. As long as the number of measurements is roughly equal to the number of unknowns, you should be able to invert whatever that relationship is and compute the 2D reconstruction from the 3D set of views. It's just basically, you're trying to solve an equation of the form y equals ax. X is the unknown image, okay? A is some matrix because that represents a linear transform, and y is the measurements. As long as y has the same dimension as x, you should be able to invert A, right? So that's the essential idea, and we'll talk about that in a lot more detail. But the problem is you don't really have something. You don't have these directly. What you have is that you have an X-ray source, and the X-ray source passes through the material. If you make a simplifying assumption that it's like passing through like an optical, like a straight line, it really doesn't go through a straight line because there's all kinds of physical effects like diffraction and so forth. But we'll just pretend that it goes through a straight line, okay? Then it comes out in the other end, and you detect it, okay? And then what will happen? So how is your measurement here related to the thing you really wanted to know, which is the integral through the density of the object? Well, it turns out there's different physical effects for different applications. But for what's called a transmission CT, what you do is you measure the attenuation, and now you can derive an equation. Okay, the answer is going to be that you take the negative log. Because the denser the material is, the more attenuated y is. So this thing here, this usually what happens when you have a CT scan, this object here, the value of what we're calling f of xy is the density. So f of xy gets larger as the material gets denser, right? But here, as the material gets denser, y gets smaller. So they're going in the opposite direction, right? This attenuates the signal as the material becomes denser. But the thing you need mathematically to do the reconstruction gets larger as the density of the material gets larger. So they're in the wrong direction. So the answer is that you take a negative log. A negative log actually a log is a monotonically increasing function, but negative log does a contrast reversal. So let me explain that in a little more detail. So we have 45 seconds left. I'll go over this next time. But there's a differential equation that relates the absorption of the X-rays as they pass through the material. You can solve that differential equation, and you get this expression right here. So the thing you really want to know, mu, is related to an exponential. To invert that exponential, you take the log. So the thing you really wanted to know is the negative log of the attenuation through the material. Okay. That's a really key important point because it means that transmission tomography problem is a nonlinear problem. Okay, but we linearize it. Okay, so I think we're out of time now. I'll pick this up on Wednesday. And then if you have questions, like I said, email them. Bye.